So it's about rotational dynamics I am asked to talk about. Now before going into rotational dynamics, let me talk a little bit about so-called particle dynamics. You all know particle dynamics. For one single particle of mass m, I want to know its position as a function of time. Where does it go 10 seconds later or 20 seconds? Okay, good. So S equal to ut plus at square. Now this is a particle for which already there are some commitments. What are those commitments? Constant acceleration, constant force. Okay, I want minimum restrictions. I just have a particle of mass m and I want to know its position, its velocity, its acceleration with minimum restriction that force should be uniform, force should be constant, this and that. So what is that basic equation then? V is equal to ds by dt. Okay, V equal to ds by dt. Now tell me, is it a law under certain situations, under certain conditions? Is it a law under certain conditions? There's a difference between these two, character of these two equations. The first one is law. The first one is law. It comes from, if you have a uniform force, so that there is a uniform acceleration, from there, yes, the first equation comes. But the second one, V equal to ds by dt, it is just the definition of velocity. ds by dt is called, it's not a law of nature. Somebody has coined a word velocity for this quantity, right? The laws of nature are not made by me, not made by you, not made by Sir Isaac Newton, not made by Albert Einstein, not made by Robert Hooke. They are made by nature. By nature, right? We only discover. But V equal to ds dt is not a law of nature. It's a definition. Someone has said that, okay, let us call this quantity V, symbol V or symbol U something, and let's call it velocity or speed or blah 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 blah. Okay. For a single particle, the equation which will give me all those things is F equal to ma. Or F is equal to dp dt. What is P? What is its expression? Which one is the law of these three? Second one? First one. What about second one? Second is the law. And first one? Is also a law, right? That linear moment, if you know what is linear momentum, if you know what is force, the law is that force is rate of change of linear momentum. If you know what is acceleration, what is mass, what is force, the law is yes, mass into acceleration will be equal to. It's not that mass into acceleration is known as. It's not that dp dt is known as. It's a law of nature. Linear momentum, if changes, and if you know the force, there are laws for force. F is equal to capital G m1 m2 by r square, or q1 q2 by 4 pi epsilon naught r square. So if I know how much force is there on a particular particle, and if I measure the acceleration, or if I measure the linear momentum, I will find that yes, F is equal to dp by dt. It's a law of nature. Or F is equal to mass into acceleration. It's there. But P equal to m into V, that's the definition. That's the definition. P equal to mv is a definition, right? And under this definition, the two laws 1 and 2, F equal to ma and F equal to dp dt are same. Right? If that is law, this is law, this is law, that is law. They are same. They are identical. It's the same expression. Then comes system of particles or a group of particles, not a single particle but more than one particles, like a two charge system, a charge q1 here, a charge q2 here, they are attracting, and maybe from outside there is a capacitor, this, that, so because of this there is a field and there is a force on it, because of all this capacitor, etc., there is another force on it, and so on. It's a group of two particles, right? So you can talk of group of 10 particles, 100 particles, 1000 particles, 3 particles, and so on. Now there are two kinds of forces. Forces by the particles belonging to that group, that q1 is exerting on q2, q2 is exerting on q1. Those are those we call internal forces, because I am talking that whole thing as a group. Once you define group, then you know what is internal, what is external. And then you have external forces which are coming from sources beyond the group, right? For that also you have certain equations. Of course, that if you individually treat each particle separately, F equal to ma is good enough, right? But then for those two particles taken together as a group, then also we have some equations you may be knowing. If I look at this external forces, then there is a total external force on the whole group, that is once again dp dt, where P is now for all particles MIVI. It works, right? And then if you know what is center of mass, how many you know what is center of mass? Oh, not many. Okay. So if you have a group of particles, at a particular instant, there are certain fixed positions for those at a particular instant, specified positions of all the particles. Then I can also get to know position of a very special point in the group, which we call center of mass, right? And qualitatively, if this is center of mass, you should have masses on this side, you should also have masses in this side. If you have masses on this side, you should also have masses, not equal, not necessarily equal. But this will not happen. The center of mass is here and all the mass is on this side. That will not happen, right? So that way the word center is significant, that it has to be a point so that mass is distributed not very symmetrically, but at least on both sides. If there is a mass here, there should be a mass on this side also, right? There are some mathematical definitions. I will not talk much about center of mass. And then this equation can also be written as F external is equal to total mass. This is the total mass of the group times acceleration of the center of mass. So these are the laws, these are the equations, not independent. You can derive all these things from the basic F equal to ma for a particle, but these are the equations which govern the system, right? Now the group of particles, there is a special category called rigid body. Okay, group of particles means just like two charged particles, one can come here, one can come there. That's not rigid body. But then there is special group of particle or special class of group of particles which is called rigid body. Now tell me, what is a rigid body? The whole board is rotating. Okay, so what I have to do, I have to put a hand here and then I rub so that it doesn't go back. Once I know the laws for rotational dynamics, all these things I will understand better, right? If I rub it here, it's going back. If I hold it here and then rub, it's okay, nothing happens, right? So all those things we will understand if I know these laws of rotational dynamics. So what is rigid bodies? What was, you were saying something? Yeah. Distance between any pair of particles of that group should not change with whatever you do. apply forces or let it move, or right. So if I have a rigid body, if I have this pen body, and if I take this point where this letter O is written, I take another point where this red thing camelin is written, more specifically C is written, or even one single point of that C. So if I take two particles on this pen body, I can throw it, I can rotate it, I can put it in my pocket, but I should not open the cap. Okay. So as long as I am not opening the cap, the distance between this particle and this particle remains same, and that happens for any pair of particles of this group, not the ink. I am talking about the body only. So that kind of body can be treated as, can be called as rigid body. If I want to be mathematically very correct and rigorous, etc., etc., then nothing is rigid body. I can always hit a hammer on it, and the distance between the particles will change. Right? So nothing is rigid. But for the application I am doing, during that application, if the distances are not changing, for me it is a rigid body for that application. Okay? So we will talk of these rigid bodies. So rigid bodies move, that means that group of particles is moving, right? And in that also there are some special kinds of motions which we have given names. One is what we call pure translation. Now I am not talking of a particle, I am not talking of a group of particles in which the separation between the particles can change. I am talking of rigid body, extended body, and pure translation of this rigid body. What do I mean by that? Movement of the body is in straight line.
Can move in any way. The movement of the center of mass is what represents like the motion of the entire body. It's not like the position of other particles with respect to the mass change.
It can move in any way, but the center of mass should move in a...
No, the center of mass, the motion of the entire body can be described as the motion with the motion of the
That's
center.
fine, but what is pure translation? Which kind of motion is called pure translation?
Linear.
You said that all the particles should move in straight lines.
No,
Center of mass should move in a straight line. Without any angular momentum. Without any rotation. Okay? Yeah.
I got it.
Yeah, tell me, I will repeat, don't worry.
Velocity of all the particles should be equal.
Velocity of all the particles should
In the
be
body.
equal.
Equal.
Should be equal.
Yes.
Okay. Now I am showing you a motion, and tell me whether it is pure translation or not.
Yes. The orientation is changing. Yes, it is pure.
The particles are not rotating.
No, it is pure translation because the orientation isn't changing.
The whole rigid body. Once it is rigid body, I can talk in terms of particles also, right? But the pure translation means not pure translation of this particle or that particle. Whole body. Okay. Now I take that definition. If at any given instant the velocities of all the particles are same, and when I say velocity this time I mean its vector character also. The direction of velocity of all the particles should be same. The magnitude of the velocity of all the particles should be same at a given instant. If you go for the another instant, it can be different. But then at that instant, everything should be same. Right? We call that pure translation. If it goes from here to here, it's a pure translation. Everything is going with the same velocity. If it goes like this, it is pure translation. It goes like this and then it goes like this. That is also pure translation. At any instant. At this instant, everything is going this way. At this instant, everything is going. At this instant, everything is going up. So at any given instant, all the particles are going with same magnitude of velocity, same speed in the same direction. We call it pure translation. Now when I am rotating it this way, at any instant, look at this instant, everything is going in this direction, everything. Look at this instant, everything is going in this direction. Look at this instant, everything is going in this direction. It's a pure translation. Okay? Then there is another class of motion which we call rotation about a fixed axis. Okay, this is another class of motion of rigid body where I say it is rotating about a fixed axis. So axis is a straight line, right? So there is a straight line which we will be calling axis, and the rotation is about this fixed axis. Means there are several things, carefully note. One, each particle of the rigid body is going in a circle or a circular path, not uniform circular motion, right? Not necessarily uniform circular motion, but the path is a circle or a part of the circle, right? So each particle goes in a circle, each particle of the rigid body. The centers of all these circles lie on this axis, and a plane of these circles lie perpendicular to this axis. If these three criteria are met, what are the three criteria? First, tell me. Perpendicular to the axis. What? Complete the sentence. He says perpendicular to the axis. That's not the criteria. What is the criteria? All particles should move in circular path, right? All particles must move on circular path. It is not necessary that they complete the circle, not necessary, but their path is circle, part of the circle. Okay, so the first criteria is all the particles of the rigid body must move with in circular paths. Second criteria, plane of all the circles should be perpendicular to that line. Good. And third one, all the centers of all the circles must be on that axis. If these three are met, okay, you can be sure that it is rotation about the fixed axis. Now, yeah.
So can the axis be outside the body?
Sure. No, absolutely no problem.
But then that way wouldn't the movement with a block also qualify as rotational motion? Because that also, if you plot it, then each point is moving in a circle and it's moving about the fixed axis that way, and it's moving about a circle that way. So wouldn't it qualify as well?
I have no objection.
So the motion of the block that way is also is rotational
Oh,
motion.
this motion that you
Yeah,
are telling.
yeah.
Okay. 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 Come. And then give me where is your axis of rotation. This is your axis. Give me the place. There. Okay. And what is the condition of this block after it goes this side? Does it go like that?
Yeah.
Okay. So this point, the distance of this point is this much here, and the distance of this point is that much here. All right. So it is not going in a circle with center on this line. Otherwise, this distance should have been equal to that distance. Right?
But what about the center of mass?
I am not talking of center of mass. Pure translation means all the particles should go with the same velocity at any given instant. And pure rotations means all the particles should go on circles, and all those centers of the circle should be on that line, and all the planes of the circle should be perpendicular to that line. Right? So center of mass will do something, let it do something. Right? Now let me do some, I am showing you some motions, and tell me, do we have some pendulum? Yeah, I think I have. I have this pendulum, okay, and the pendulum swings. Is it a pure rotational motion of this rigid body? This bob is a rigid body for my application, okay. So look at this, look at the motion of this rigid body, the bob. Does it qualify for pure or rotation about a fixed axis? And where is that axis of rotation? This one, right? So all particles of this will go in circles, and all the planes of these circles will be perpendicular to this axis, right? And the centers will be on that axis. So it is a rotational, pure or rotation about this fixed axis, and here is the axis, right? Okay. Now, come. Yeah, please. Now, you don't have to speak any word, okay? You can answer my question just by checking your head. Look at the camera. Are you a student of class 11? Was this a rotation about fixed axis? Where was the axis of rotation? Vertical. Good. All the particles were going in circles. Notice. Right? All the particles are going in circles, circular paths. Okay? And all those plane of circles are perpendicular to this. They are horizontal. All that circular paths are horizontal. So circles are horizontal. And all the centers are on that line. Okay? Are you a student of class 12? Is this a pure rotation? Where is the axis of rotation? This is the axis of rotation, horizontal. Right? This is the axis of rotation. So these are the circular paths. And the centers of those circular paths are here, and the line perpendicular to that plane, the plane of the circles, that is this fixed axis. Now in Maharashtra, if you go, and if you ask some question, and the person has to answer in affirmative, yes, normally he has done like this, but in Maharashtra, you know how people do? Okay, good. Where is the axis of rotation?
It's this way.
Yes, it's this way. My circles are like this. My circles are like this. They have to be perpendicular to the axis of rotation. So this is rotation with this as the axis. This is rotation with this as the axis. And this is rotation with this as the axis. All x, y, z axis. Now tell me, I am giving you some motion and you identify whether it is a rotation about a fixed axis. If so, where is the axis of rotation?
Yeah.
Where is the axis of rotation?
Yes, where the not two places, two axes.
No, there cannot be two axes. My definition says that there should be a fixed axis of rotation, one single axis of rotation.
So there are two systems.
Two
then.
separate systems.
Yes, this is not a rigid body. In this motion, this is not a rigid body. Look at the distance between these two tips. It's changing. Okay, so the question does not arise. It's not a rigid body motion, and therefore these qualifications cannot be made. All right. So this is about the nature of what we call rotation about fixed axis. All right. Now, what are the defining dynamics? Now, I want to do dynamics. Dynamics means what? As a function of time, where the thing is going. Right? If I am rotating my hand PT. It's a pure rotation. Where is the axis? From here perpendicular, right? So if I want to know that at this time it is here, at 1 second after where it will be, after 2 seconds after where it will be. So that's the dynamics in particle, where the particle is as a function of time, here where this whole rigid body is as a function of time. So first thing is, for a particle to define where the particle is, I need its just distance from the origin, x. If you tell me the value of x, I know that okay, the particle is here. If it is in 3 dimensions, x, y, z. If it is on a single line, then it is just one coordinate x. In a rigid body, I want to define the position of the rigid body. Position means a position of every particle of the rigid body. Then I say that okay, I know where this rigid body is, how it is oriented, everything about that rigid body. What are the quantities I should look for? Just like for a particle, if I say where the particle is, I would like to ask what is the value of x, what is the value of y, what is the value of z, given x, y, z axis and origin. So here also I give you x, y, z axis and origin, and it is that fixed axis rotation. So that axis you take at z axis. So I have given you z axis, I have given you origin, I can also give you x, y if you so like. And then I want to know at this instant, the rigid body is like this. So what are those quantities that I should specify, and how many of them I should specify? For a single particle there are 3. For this rigid body, how many? This is a rigid body. This is here. At this instant it is here. I have given you some x-axis, y-axis, z-axis and all that thing. This rigid body can go anywhere in any fashion. Okay. In space I have an origin, I have x, y, z axis. So what quantities I give you, which coordinates or what quantities, so that once those quantities are given, the numerical values, it is fixed. And one can say that yes, it is here and in this orientation. And how many of such quantities will be needed? So,
Time?
yeah, at a given time, it is here. Let's say it is here. But then I want to specify it in terms of minimum number of x, y, z, theta, phi, delta, epsilon, this, that, minimum number of parameters. So that once it is here, I know that x is this, y is this, z is this, theta is this, phi is this, epsilon is this, delta is this, gamma is this, beta is this, alpha is this, and then it has gone here. So the x has changed from this value to that value, y has changed, beta has changed, alpha. So how many those quantities x, y, z, alpha, beta, gamma, delta, epsilon?
So velocity of that particle at that time, of the particles moving along in that rigid body at that particular instant.
See, my problem is this has got millions of particles. I cannot keep track, right? Okay, center of mass I can perhaps keep track, yes. So where is the center of mass? For that I need x, y, z of the center of mass. If you tell me that this is x coordinate, this is y coordinate, this is z coordinate of center of mass, then I know that okay, center of mass is here. Center of mass is now fixed. But then with the same center of mass, it can be this way, that way, that way, that way, that way. So my rigid body's position or configuration is not completely specified by specifying the center of mass. So 3 coordinates will fix the center of mass. Now it cannot be there. It is here. That is fixed. But then this orientation or this orientation or this orientation.
So is it the axis of rotation about which?
I'm now talking of very general motion. It can go this way, that way. So there is no rotation about a fixed axis. I have origin, I have z axis, I have x axis, I have y axis, right? And then it is moving in any fashion. Yeah, orientation. I have to fix the orientation. Yes. If I know coordinates of any 2 points, we may be able to fix. Now let us say this corner and this corner. All right. So these corners, this corner and this corner. Let's say I know the coordinates, I know the positions. But then it can be like this, with the same 2 corners fixed. It can be like this. It can be like this. Okay, right? Right? So I need one more angle, rotate it. These 2 points are fixed. If these 2 points are fixed, all points on that line are fixed. If these 2 points are fixed, anything in between cannot move. Otherwise, the distance will change. If 2 points are fixed and the third particle is somewhere on that line and you move it anywhere in any direction, its distance from these 2 fixed points is going to change. So if it is a rigid body, that will not happen. All these points are fixed. Therefore, this becomes the axis of rotation effect. Anything can only go in circles about that, because once again, the distance of each particle from each other particle has to be fixed. So if this whole line is fixed and a particular point here is fixed, other point is here, the only way it can go on a circle, otherwise its distance from it will change. Right? So all particles are now going in circles with this as the axis of rotation. If 2 points are fixed, it is a rotation about fixed axis. And that fixed axis is nothing but the line joining these two. And all particles on that line, falling on that, will be fixed, will not move. And all other will move in circle. So if all other are moving in circle, start with some configuration, call it theta equal to 0. And how much I have rotated? Just give me that angle. Done. So 3 coordinates for this corner, 3 coordinates for this corner, 6, and plus 1 angle. If these 7 quantities are given, then the orientation, the position, everything will be fixed. But do I need 7? Or it's more than enough? It's surely enough. But is it the minimum? When you fix up 2 particles, you specify 3 coordinates here, you specify 3 coordinates here, you specify 6 coordinates, and then the 2 points get fixed. But then the distance between these 2 points is already there. If they are 7 centimeters apart, they are 7 centimeters apart. So your x1 minus x2 whole square plus y1 minus y2 whole square plus z1 minus z2 whole square must be 49 centimeters square. Right? So if you give 5 of them, the 6th one I will get from this equation. So I don't need 6, I need 5 to fix up 2 points and then 1 angle. 6 quantities are needed, just 6 quantities are needed to fix up the position of these millions and billions of the particle of the rigid body in any kind of general motion. Right? So that if you can specify, fine. But let's come back to this rotation about fixed axis. Now the axis is fixed. Now I need only 1 quantity. From some given configuration, starting configuration, how much any particle has rotated from there, how much angle. Each particle has to go on circles. So that radius, how much angle it has rotated. And all particles has to rotate by the same angle. Just give that theta. So it's like your one-dimensional linear motion. Just give me x, I know where the particle is. Here just give me theta, I know where my rigid body is. Yes? Yeah, please repeat.
I was saying that won't you also need to know the distance of a particular point from the axis?
Okay. Why do I need that? If 2 points are fixed, axis of rotation is known, right? Now it's a rotation about that same fixed axis. And I say that this is my starting configuration. As you say, at t equal to 0, the particle is here. At t equal to 0, the orientation is this. And then at some time t, the orientation has changed. But this line is fixed. Axis of rotation is fixed. I can only rotate it this way, nothing. I cannot do anything else. And if I know this angle, suppose it is, let's take this as the axis, the central. How much I have rotated? 90 degrees. Just if I tell you I am going to rotate it 90 degrees, Don't you know its final configuration? It has to be like this. Okay. Now watch how much I am rotating it. So just give me the angle and I know where it is going to land. I don't need any other distance. Okay. So one coordinate is needed, angle through which any radius, each particle is going in circle. Pick up any particle, one particle, and see what is its radius and how much this radius is rotated. That angle is called the angle of rotation or angular position from that starting t equal to 0, that we take theta equal to 0. From there, this is the angular position. Okay. So the position is described in terms of one single quantity, and that is the angle of rotation. I have this axis, I have a body, pick up any point and drop a perpendicular. Why did I draw this peculiar perpendicular? It doesn't look like 90 degrees. Yeah, I am allowing the particle to be out of the board, and from there I am drawing this perpendicular. And so this is going in a circular path. This is the center. Here is the center. I have dropped the perpendicular, remember. So this is the center, and with this as the center, it is going in a circular path. I don't know how to draw. This plane has to be perpendicular. Okay. This is outside the board, something like that. So it is going like this. Now this is the radius at t equal to 0, and at some other time this, because this goes here, and this angle theta, is it too small? Can you see it, this theta? Can you see this theta? Okay. So if something is going, and this is the axis of rotation, okay, if this is the axis of rotation and it is rotating like this, take any particle, draw a perpendicular, that's the center, look at that circle, look at that radius, and then in time t, how much that radius has rotated. Pick up that, that is theta, and that decides completely the position. Okay. Now once you have theta, now definitions, not laws. I define angular velocity as d theta by dt. The rate at which this theta is changing is called angular velocity. Dx by dt is called velocity. D theta by dt is called angular velocity. You pick up any direction on the x-axis and say that this is the positive direction. Right? That is your choice. Similarly, here you can pick up, there are two kinds of rotations possible with the same axis. Looking at the top, this can go clockwise, this can go anti-clockwise. Pick up any of that as positive. The convention is, if you are looking at that rotating body, and if the radii are going on, the rotation is anti-clockwise, you take that as positive rotation. But remember, you can see it from the top, you can see from the bottom. If it is clockwise from top, it will be anti-clockwise from bottom. So this is not a good convention, right? So what we do is, we say that we give a direction to the angular velocity itself. And how do we do that? Look from top or look from bottom, doesn't matter. If you find the rotation as anti-clockwise, right, that means I am standing so that my line of vision is perpendicular to that circle, then only I will talk in terms of anti-clockwise, clockwise. If there is a circle and I am standing here and the particle is going like this, how do I call it anti-clockwise or clockwise? I have to come this side or that side. So I am already along the axis of rotation, so that particles are going in circles and that plane is perpendicular to my vision, line of vision. Now if it is anti-clockwise, we say that the direction of angular velocity is towards me. If it is clockwise, it is away from me. Okay. So I have something which will rotate. Let us take this one. Let us take this one. And for this side, I am on one side, and these people are on the other side. Now, you people tell me, it is clockwise or anti-clockwise? You people tell me, it is clockwise or anti-clockwise? So from this side, it is anti-clockwise. What is the rule? If you find it anti-clockwise, the direction of angular velocity is towards you. So it is in this direction. The angular velocity is in this direction. It is clockwise. What was the rule? If it is clockwise, it has to be away from me. So what is the direction of angular velocity? So no problem. Look at from this side, look at from this side. Your angular velocity direction is same, uniquely determined. All right. So that is how we define the angular velocity vector. Okay, we call it angular velocity vector, omega. The magnitude is given by this, and the direction I have already told you how to determine. Okay. Then you define alpha is equal to d omega by dt. You can put a vector sign also. Angular acceleration, angular velocity, angular acceleration. These are all definitions. Okay, the law comes, the dynamic comes when I say how that angular acceleration is produced. Okay, v equal to dx by dt is just a definition. A is dv by dt is just a definition. The law starts, the dynamics starts when I say to create an acceleration of this particle, I have to apply a force, and that force will be equal to mass times acceleration, right? Then the dynamics, rule of dynamics, law of dynamics comes in. So these are definitions. Now my question is how to create an angular acceleration. Okay, so any door which I can open, will this open? Yes. All right. Okay. Now here is a rigid body, right? This whole door is a rigid body, and if I move it, it is a rotation about fixed axis. Where is the axis? Through the hinges. This is the axis. At this time, what is its angular velocity? 0. Nothing is moving. No angle is changing. It can go on that circle, but it is not going. Right? So the angular velocity is 0. Now what happened? Angular velocity was created. Upward or downward? Upward. Look at the circles. Look from the top. Look at the circles. Towards me. So up. So the angular velocity is in the upward direction, vertically upward direction. Angular velocity was 0. Now the angular velocity was created. So there was an angular acceleration in that period. And to create that angular acceleration, what did I do? I applied a force. Okay. So if I apply a force, angular acceleration, or let me write it this way. Acceleration, force must be applied. F is needed. I am applying to the best I can do same force on this door. I will apply it twice and I will try to apply the same force. So I apply it here, and the same force I apply it here. What about visibly? Can you see? Can you compare the angular acceleration, which is less, which is more? Okay. The same force can create different angular accelerations. So acceleration is not proportional to force alone. It depends on the distance from the axis. All right. So Force is needed, number one. So it depends on force. Then it depends on distance r from the axis. Okay. Once again, I am going to apply a force. I'll try to apply a force of the same magnitude, but it's not very necessary also. But at the same place. In two situations, compare what happens. I am applying a force here at this corner. Okay? At this edge. I am applying a force very hard at the same corner. Can you see what I am doing? Look at this top. See? At the same edge I am applying a force. No angular acceleration. And now at the same edge I am applying a force. Same distance. Same magnitude of F. Same magnitude of R. And right, same place. Same magnitude of R. From that hinge line, I am at the same distance. I am at the edge of the door. Direction. The same force at the same place, but whether it is perpendicular to that door, whether it is parallel to the door, whether it is parallel that way, at the same place, I am applying a force vertically upward. Okay, I am applying a force vertically upward. No angular acceleration is produced. So it depends on F, it depends on R, and then the component which is parallel to the axis will not do anything. If I apply a force, its component parallel to the axis of rotation, it will not do anything if that axis of rotation is fixed. The perpendicular in the horizontal plane, in this case, horizontal plane, there I have to see what is the angle. Okay, angle of that force. If it is perpendicular to the axis and perpendicular to this radius, then the angular acceleration is maximum. And if it is at some other angle, if the component which is along the radius is again not going to play any role. Only the component which is perpendicular to the radius and perpendicular to the axis of rotation, only that is going to play a role. So first thing, you forget about that component parallel to the axis of rotation. Forget that z component, you forget. Then in xy plane, you see what is the angle of your force with this F. Right? So the angular acceleration is proportional to 2 times, I have to write alpha, r into F into sine theta. What is this alpha? And what is this alpha? Directly proportional to. So angular acceleration is directly proportional to r. If you go away, yes, the acceleration is more. Proportional to F, if you apply a harder force, it's more, yes. Then it is proportional to sine theta. Why sine theta? Why not? How I define theta, it will depend on that. So if theta is equal to 0, so I am taking radius as the line, that is theta equal to 0. If theta equal to 0, along the radius I am pushing, nothing will happen. So at theta equal to 0, this acceleration has 0 value, so sine theta. At 90 degrees it is maximum. Correct? So it is r into F into sine theta, where theta is the angle between r vector and your force in that plane perpendicular to this axis. That is theta. Now, remember any expression which has r, which has F, which have sine theta? Cross product. Cross product of two vectors, r vector and F vector, the magnitude of this, that will be r into F into sine theta. A vector cross B vector. What is it? AB sine theta. So if I write it in vector form, here is the body, rigid body. This is axis of rotation, and then I take a particle I drop a perpendicular here, and this I call r vector. This is the point where I will be applying force. And in that perpendicular plane, with this r vector making angle theta is the F vector. And r cross F, magnitude of this is r into F into sine theta. I am forgetting the component parallel to the axis of rotation, that has nothing to do in this. Okay. Now this is the quantity which directly determines the angular acceleration. Force is the quantity which directly determines the linear acceleration. Acceleration A is proportional to force. Here angular acceleration is not proportional to force alone, not proportional to r alone, not proportional to sine theta alone, but it is proportional to product. So this quantity we write it as gamma equal to r cross F is called, what is it called? Torque of force F about the about the origin, in fact. This is law or this is definition? This is definition, yes. This is only definition. The law is going to come now. But look at the complete sentence. Just don't call it torque. The complete sentence is torque of F about the origin. From where that r vector is measured. Right? You can have 2-3 forces on the rigid body. In fact, on this door also, there were several forces, not only the force which I applied. What were the other forces? Gravity. But that did not have any role in this rotation. Why? It was parallel to the axis. It was parallel to the axis. Then there were hinges. Hinges were applying some forces on the door. Right? But at this moment, it's not doing. It's along the radius. It's along the radius. Correct? If it is parallel to the vertical axis, that hinge axis, no problem. If it is parallel to the radius, no problem, theta will be 0. Only if it is perpendicular to this radius and also perpendicular to that axis of rotation, only then it will come. So from hinges, you have forces in vertical direction. From hinges, you have forces parallel to the door. But then those things are not contributing, only my force is contributing. Right? That was but then I can also apply force at 2-3 places. If there is a big heavy almirah and it is to be pushed, one person is not able to push, so several persons push from several points, they apply forces. So the torque to be calculated for angular acceleration is combined torque of all these forces. That's the resultant torque. Then these particles are interacting inside each other. It's a group of particles, remember. It's a solid, it's a rigid body. So these particles must be interacting among themselves, otherwise it will be a gas. If these particles do not interact with each other, how will they maintain the shape? It will be a gas. And those internal forces will also have torques. But then that total internal torque will come to 0. So it is only the external torque which is important to calculate all these accelerations so on. Okay, so that is what is the proportionality constant? That has to be worked out. It is not F equal to ma. F is proportional to A, you put m there. Here this torque is proportional to alpha, you have to put something there. Not something you have to put is, I am exclusively talking fixed axis of rotation. torque external z component. Torque is a vector quantity r cross f. So you can take components. Only take component parallel to the axis. I told you force parallel to the axis will not produce any angular acceleration. But now I am talking of torque. Look at the direction of torque. This is r vector. Okay, and this is f vector. What is the direction of r cross f? This is r vector and this is f vector. So r cross f upward. So torque vector is parallel to the axis of rotation, and only component which is parallel to the axis of rotation, that will produce acceleration about that axis. So remember, force parallel to the axis of rotation will not produce angular acceleration, but torque parallel to the axis will produce this angular acceleration. Okay? Torque will have other directions, but that will not produce angular acceleration about this axis. If this axis is fixed, all those other things are not usable. That's why I am writing this gamma and z in suffix. Only look at the z component, and that is equal to a proportionality constant. People write it I and times alpha, and this I, they call it moment of inertia. About the axis, and how do I calculate it? It is for each particle of this rigid body. Now you see particle by particle. Each particle of rigid body, what is the perpendicular distance from the axis? Square it, multiply it, and then add for all the particles of that rigid body. This Ri is the perpendicular distance from that axis of rotation. Mass of the particle, perpendicular distance from the axis of rotation. Square, multiply, and add for all the particles. This is the quantity which will appear here. That is the dynamics, that is the law, that what is will decide where this body will be after time t. Okay? So I think we can take break here.